Let's talk about subroutine and create a delay function. So one thing to notice here is the SPL and SPH registers are in the first 64 instructions of the I/O memory. So we can use in and out instructions to store and load data from them and to them. To use subroutines in the program, first we need to initialize the stack pointers. So first what I did is I loaded R16 with the value of highest point of the RAM address and its high byte. Then it's stored in the SPH register. Remember, SPH is in the first 64 I/O registers, so we can use out here. In R16, I loaded the low byte of the highest RAM address. So this is a function, and this is a defined constant. So for ADMega32, its highest point in the RAM is stored here. The address is replaced here. And for other devices, that specific value is stored. I stored the R16's value in the SPL. So the stack pointer is initialized here. Let's write a subroutine. Let's write a general delay function first. An important point for subroutine is we have to include the return instruction here. So what it does is, first it loads with the value of 255 FF. For the decimal value of FF is 255, and then it gets decremented one by one, and after that, when the R17 is 0, it returns from the function. So to call the function, what we need to do, we have to use the call instruction and mention the tag here. So let's visualize the program. First, let's build it, and then we will debug it. So first, in the data IRAM, R16 gets 08, the high byte is 08. Then if you see in the SP, here you first have to choose CPU register, this one in the IO panel, and look at the SP. If I step into, so the high byte is 08. Then the low byte is 5F. So 5F gets loaded into R16. So then if I step into, the SP is loaded with the highest memory location for ADMega32. If this instruction gets executed, the program action goes here in the function. Then the R17 register is loaded with the value FF. It will decrement, and it will continue decrementing until the value is 0. So if I continue, and let's put a breakpoint here. So if I continue the execution, you see when R17 is 0, it gets here, and then if I step into, it will go to this instruction, because after call the delay is used. So actually what we need to do is we will call it loop, and we should jump to this loop indefinitely, because the next instruction should be loop, not the delay here. So this is a never-ending loop. So let's try again. Let's build the project, and let's create a breakpoint here. And then after it gets to return, it should go to this instruction. It gets here in line number 19. Then again it calls call delay, because it says, this instruction says jump back to loop, and the first instruction in the loop is call delay. So now let's create a specific time delay. Let's say we want to create a delay function of 250 microseconds. How can we do that? So for that, we need to do some calculations. Similarly, to increase the value of delay, we can create nested loops. Let's say here, so increase the amount of delay, we can use nested loops. So let's see how we can do it. So here I have created a nested loop. There are 3 loops. Inside L1 there's L2, and inside L2 there's L3. Let's calculate how much time or how much cycles, machine cycles, are needed to execute the whole delay function. Let's start with the L3 loop. The knob, it's just a dummy instruction, it does nothing, and it takes 1 machine cycle. So 1 and 1. Decrement takes 1 machine cycle as well. And then the branch if not equal instruction, it takes 2 machine cycles if the execution gets branched. And if it's fall through, then it takes 1 machine cycle. So overall, for each execution of this L3 loop, it takes around 5 instructions, 5 machine cycles. So for simplicity, ignore these machine cycles. Let's calculate the whole thing. So 5 instructions for L3. L3 gets executed 10 times, and L2 gets executed 255 times, and L1 255 times as well. So if we calculate the machine cycle, it's 10 times 5 machine cycle is 50, then 255 for L2 and 255 for L1. So the delay function actually executes this amount of machine cycles. So let's convert it with the time. Generally, by default, the ADMega32 runs in 1 megahertz clock speed. So each machine cycle needs 1 divided by 1 million second. So it's this much second. So let's just multiply this value, the last the total machine cycle in the delay function and multiply it with this value. So if I multiply it with this, so the function we have written, it's actually delay for 3 seconds and 25 into 25. So this much second is the delay amount we have written. So let's just adjust it a little. Let's say we want 250 and 10. $250 and 10. So the calculation will be 10 into 50 into 200. So if we multiply it with this value, we get 1 millisecond, 100 millisecond, and 100 millisecond. Multiply, if we make the L3 loop run 25 times, we will get a decent 250 millisecond of delay.